Welcome back to Signal 2030, where we explore the scientific breakthroughs shaping our future. In part one, we explored the science behind fusion, the physics of ignition, the triple product, and why this challenge has captivated scientists for decades.
That's right. Here and continuing in part three, we turn our attention to the first of two main approaches to make fusion a practical energy source. From magnetic confinement in massive tokamaks to the precision implosions of laser-driven fusion, we'll break down how each approach works, the hurdles they face, and the companies racing to make fusion a reality.
So when we look at the global efforts to achieve fusion, to hit that magic number, you basically see two completely different strategies emerge, right? Almost like two competing philosophies.
That's a great way to put it. They represent radically different strategies to climb the same mountain to achieve that required triple product.
Okay, what are they?
On one side, you have magnetic confinement fusion, or MCF. This strategy basically tries to achieve the triple product by aiming for very long energy confinement times, potentially seconds, minutes, or even continuous steady-state operation in a power plant. But it does this at relatively lower plasma densities,
Typically around 10 to the 20 particles per cubic meter.
which is still a pretty good vacuum by Earth standards, but low for fusion.
So MCF is like holding a hot, thin gas for a long time in a magnetic bottle.
That's a reasonable analogy, yes. Patience and strong magnetic fields are key.
And the other approach.
The other main path is inertial confinement fusion.
Or ICF. This approach takes the completely opposite tack. It pursues extremely short confinement times. We're talking mere nanoseconds, billionths of a second. But it compensates by achieving absolutely incredible densities during that brief instant.
Compressing the fuel to densities greater than 10 to the 31 particles per cubic meter.
That's denser than the center of the sun.
Whoa, so ICF is more like a tiny controlled explosion. Squeeze it incredibly hard for an instant.
Exactly. It relies on the fuel's own inertia, its resistance to movement, to hold itself together just long enough for a significant number of fusion reactions to occur before it blows itself apart.
So you've got these two completely different approaches. MCF, low density, long time. ICF, high density, short time. Each trying to hit that magic NTE number in their own unique way.
Okay, let's dive deeper into these two dramatic approaches. It feels like a real scientific showdown. Let's start with magnetic confinement fusion, the patient magnetic prisons approach.
Sounds good.
The overall idea here, you said, is using powerful, very precisely shaped magnetic fields to contain that hot but relatively low-density plasma inside a vacuum vessel.
That's the core concept, yes. The charged particles, the ions and electrons in the plasma are forced by the magnetic field lines to spiral along them. If you shape the field correctly, you can guide these particles and keep them away from the physical walls of the reactor.
Because touching the walls is game over.
Instant vaporization, yes. So the magnetic field acts like an invisible bottle. Now, within MCF, the undisputed workhorse, the one we hear about most, is the tokamak, right?
Absolutely. The tokamak, which originated in the Soviet Union back in the 1950s, is by far the most mature and widely researched fusion device concept globally. Most of the big international projects like ITER are tokamaks.
So how does it work? What makes the tokamak bottle shape?
Well, its operational principles are quite ingenious, really. It uses a combination of magnetic fields to create a twisted helical field structure inside a donut-shaped vacuum vessel. We call that shape a torus. This twisting is crucial for stability.
Twisted fields, okay.
There are two main components. First, there's a very strong toroidal field. This runs the long way around the donut. Imagine giant D-shaped coils encircling the vacuum vessel. Those create the toroidal field. It's the main confining field.
D-shaped coils making a field go round the donut. Got it.
Second, this is really the defining feature of a tokamak, there's a weaker poloidal field. This runs the short way around the plasma's cross-section, sort of like stripes on the donut. This poloidal field is absolutely vital for confining the particles properly and for stability.
And where does that poloidal field come from? More coils.
Here's the clever bit. It's generated primarily by a large electrical current, often millions of amperes, that is induced to flow within the plasma itself.
A current inside the plasma makes its own magnetic field.
Exactly. The plasma acts like the secondary winding of a transformer. There's usually a large solenoid coil running down the central hole of the donut. By ramping up the current in this central solenoid, you create a changing magnetic flux, which, by Faraday's law of induction, drives a powerful current within the plasma ring.
Okay, that's clever. Transformer action, does that current do anything else?
Yes. It also provides some initial heating to the plasma through electrical resistance. We call this ohmic heating, like in a toaster element. However, a peculiarity of plasma is that its resistivity actually decreases as it gets hotter. So ohmic heating becomes less effective at very high temperatures. It can't get you all the way to fusion conditions on its own.
So you need more heat. How?
Tokamaks rely on powerful auxiliary heating systems. Two common methods are neutral beam injection, NBI, where you accelerate ions to high energy, neutralize them so they can cross the magnetic field lines, and then shoot them into the plasma, where they reionize and transfer their energy through collisions.
Shooting hot atoms in.
And the other main one is radio frequency, RF heating. This uses antennas to launch electromagnetic waves into the plasma at specific frequencies that resonate with the natural motion of the ions or electrons, pumping energy into them, kind of like a microwave oven.
Okay. And sometimes these heating systems help drive the current too.
Yes, some of these NBI and RF systems can be configured not just to heat, but also to push the electrons along, helping to sustain the plasma current non-inductively, which is important for achieving longer pulses.
And tokamaks have had some real successes, haven't they? You mentioned JET earlier.
They really have. Their key advantages are undoubtedly their high performance potential and their maturity. Decades of research mean they are the best understood fusion concept. Devices like the Joint European Torus, JET, in the UK, achieved that record fusion power output, 59 megajoules of energy released from fusion in a 5-second pulse back in 2021. That was a huge milestone.
And there was something called H mode?
Ah, yes, the H mode, or high confinement mode. That was a major breakthrough discovered in the 1980s. It's a state where, under the right conditions, a kind of transport barrier spontaneously forms near the edge of the plasma. This barrier acts like better insulation, dramatically reducing the amount of heat leaking out due to turbulence. It can effectively double the energy confinement time area.
Doubling confinement time is huge for the triple product.
Absolutely. Getting into H mode is pretty much standard operating procedure for high-performance tokamak experiments now.
But it's not all smooth sailing for tokamaks, right? You mentioned challenges.
No. Despite these successes, tokamaks come with some pretty significant inherent challenges. One is their reliance on that central solenoid, the transformer, to drive the plasma current. Transformers can only drive current in pulses. You have to ramp the current up, hold it, and then ramp it down and reset.
So they're naturally pulsed devices, not steady state?
Fundamentally, yes. While those non-inductive current drive methods we mentioned can extend the pulse length significantly, maybe even achieve steady state eventually, doing so efficiently and reliably for a power plant remains a major research and development hurdle. It adds a lot of complexity.
Okay, pulsing is one issue. What else?
Perhaps even more critically, that large plasma current itself, millions of amps flowing through this hot, tenuous gas, is a huge source of free energy. And this free energy can drive violent magnetohydrodynamic, or MHD, instabilities. These can lead to events called disruptions.
Disruptions sound bad.
They are very bad. A disruption is a sudden, catastrophic loss of plasma confinement that happens incredibly fast, in milliseconds. The plasma rapidly cools and the current collapses, inducing enormous electromagnetic forces on the surrounding structures and potentially dumping huge amounts of heat onto the walls. They can cause serious damage to the reactor. Predicting, avoiding, or mitigating disruptions is a top priority for tokamak research, especially for large machines like ITER.
Yikes. Okay, anything else?
Well, there's also the issue of neoclassical transport. Because of the toroidal, or donut geometry, the magnetic field isn't perfectly uniform. It's stronger on the inside edge and weaker on the outside edge. This variation causes particles to drift as they spiral around the field lines. Some particles get trapped in regions of weaker field and follow these wide looping paths called banana orbits.
Seriously?
Seriously, and these banana orbits can cause particles, especially ions, to drift outwards, enhancing the loss of heat and particles from the plasma core beyond what simple theories predict. It's another lost channel we have to contend with.
Okay, so tokamaks. Mature, high-performance potential, H-mode boost, but inherently pulsed, vulnerable to damaging disruptions, and have these leaky banana orbits.
Got it. Now, what about the other magnetic contender, the stellarator?
Right, the stellarator. It has a similarly long history, actually conceived by Lyman Spitzer at Princeton back in the 1950s, around the same time as the tokamak.
Yeah.
But it takes a fundamentally different approach to creating that necessary twisted magnetic field.
How so?
Unlike the tokamak, the stellarator doesn't rely on driving a large current within the plasma to generate the colloidal field. Instead, it generates the entire confining magnetic field structure, including the twist needed for stability and good confinement, using only a set of complex, externally wound magnetic coils.
No plasma current needed. Essentially, zero net plasma current is required for confinement. This means abandoning the simple, axially symmetric donut shape of the tokamak. Stellarator coils are intrinsically three-dimensional. They are intricately twisted and contorted, sometimes looking like something out of science fiction. These complex coils create a complex, bumpy, twisting magnetic field inside.
Okay, so what are the advantages of doing it that way? It sounds complicated.
It is complicated to build, but the advantages are potentially huge. First, because it doesn't need that inductively driven plasma current, the stellarator is intrinsically suited for continuous, steady-state operation. There's no transformer to reset. This is a massive plus for a commercial power plant that
Ideally needs to run 24/7.
Okay, steady state is a big deal. What else?
Second, and arguably even more important, without that large internal plasma current as a source of free energy, stellarators are inherently resilient to the violent current-driven disruptions that plague tokamaks. They just don't have the same driving mechanism for those catastrophic events.
Yeah.
This offers a significant potential advantage in terms of operational safety, reliability, and potentially cost, as you don't need such robust disruption mitigation systems.
No disruptions in steady state operation. That sounds pretty compelling. What's the catch? You said the coils are complex.
That's the main catch, the extreme engineering complexity. Those magnetic coils are not simple rings. They are incredibly intricate 3D shapes that must be designed with sophisticated computer codes and then manufactured and aligned with unbelievable precision. We're talking sub-millimeter accuracy over structures many meters in size.
Sub-millimeter.
Yes. This complexity poses significant engineering challenges, drives up construction costs, and makes assembly and maintenance very difficult. Also, the inherently 3D nature of the stellarator's magnetic field, while providing stability, can create many small magnetic wells that trap particles. This can lead to enhanced neoclassical transport, similar to the banana orbits in tokamaks, but potentially even worse if not carefully designed, causing particles to drift out more easily.
So you trade plasma current problems for coil complexity and potentially worse particle drift.
To some extent, yes. Minimizing these neoclassical losses in a stellarator requires meticulously optimizing the magnetic field shape using powerful supercomputers to achieve a state called quasi-symmetry, where the field looks more uniform from the particle's perspective even though the coils are twisted. This optimization is computationally very intensive and has really only become feasible in the last couple of decades.
So that's why stellarators maybe lagged behind tokamaks historically.
That's a big part of it. Historically, stellarators were harder to design and build, and their performance often lagged behind tokamaks. But modern computational tools have enabled the design of much better optimized configurations. And recent advanced stellarators, like the Wendelstein 7X in Germany, are demonstrating significantly improved confinement and are rapidly closing that performance gap.
The W7-X is specifically designed to test quasi-symmetric optimization
And steady-state operation.
Okay, so let's recap the magnetic showdown. We have the tokamak, mature, high performance seen in pulses, but struggles with steady state and faces the serious risk of disruptions. Requires complex control systems. Then we have the stellarator. Inherently steady state, disruption free, but incredibly complex and costly to build due to those intricate coils, and needs careful optimization to control particle losses.
That sums it up pretty well. And it feels like they're kind of converging in their challenges now, doesn't it? Tokamak research is focused on adding complexity, sophisticated real-time control systems for stability, advanced non-inductive current drive for longer pulses, disruption mitigation strategies. Meanwhile, stellarator research is focused on mastering its inherent complexity using massive computing power for optimized designs, developing advanced manufacturing techniques for the coils, and demonstrating good confinement.
So the path forward isn't clear-cut.
Not at all. The choice for a future power plant, if it's based on magnetic confinement, might depend less on the fundamental concept itself and more on which set of these complex engineering trade-offs proves to be more technologically and economically tractable in the long run. Is it easier to manage the risks of disruptions in a simpler geometry, or is it better to eliminate disruptions but deal with the extreme manufacturing challenges of complex coils?
A fascinating dilemma, and maybe a great place to end this episode. In Part 3, we'll turn to the high-powered world of lasers, capsules, and micro-explosions, where fusion happens in billionths of a second. We hope you'll join us for Part 3 as we explore inertial confinement fusion and the bold attempts to create a star with a single pulse of light.
Until next time, take care.